We can, as before, get the symbolic representation of the nonlinear system. We can linearize it. This is done. We can calculate the Fourier coefficients of all of the state space matrices. Naturally, this time we are working with a generalized time periodic representation which accounts for delays. You will recognize these matrices by having a look at the chapter 4 of my PhD thesis. Now we can apply frequency lifting. Again, I could set this to a bigger value, but I can keep it low just so the calculations go super fast for this particular system. I get harmonic state space. Naturally, this is a delayed system. The system has internal pure delays. So despite the name, this is a delay harmonic state space. Okay, I can have a look at it. DSA LTI. I have the block-to-pleats matrices, which are quite large as a consequence of the frequency lifting. I have the vector of delays. Still, there are a number of things that I can do with this delay harmonic state space. Let's start first with calculation of eigenvalues. This time, I do need to account for some options. Let's say if we have 9 states, and the number of states is naturally the same for the large signal and the small signal variables, because the number of states does not change in the linearization process. Once lifted, these states are multiplied by the number of Fourier coefficients, which gives 63 states. Well, if I put 1 here, then we will obtain 1 time 63 modes, or 1 time 63 characteristic roots. But you know that for delayed systems, there is an infinite number of characteristic roots. So if I put, for instance, 5, I will have 5 times the number of modes that I would have had if the system was not delayed. In any case, I will start with just 1. Convergence test. Yes, I would like to see if the characteristic roots have converged. I will show you what it looks like. And the epsilon, well, I will say that a characteristic root has converged if it has converged within a radius of this value. I do Control Enter, and I see that for this simple system it goes very fast. I give some information about the origin of the software for the calculation of characteristic roots of delayed systems. These are the ones that come from the computer science department of KU Leuven. So these files have not been written by myself, except that naturally the functions that call it have been written by myself. I also give some progress while using the Arnoldi algorithm. We also have the extraction of eigenvectors, and actually if you read chapter 4 of my thesis, you realize that the extraction of the eigenvectors is related to the convergence test. Total elapsed time was very small for this particular characteristic root calculation. However, please be aware that for a big system, this calculation becomes really computationally intensive. So here is the 2 results. I have one without colors. This is just the characteristic roots as they have been calculated. But then I want to know which of these have converged. They already have the characteristic shape of the eigensets of frequency lifted systems. However, to be sure which ones have converged, I see that only the green ones have converged, at least within 1 to the minus 10. The others may have reasonably converged, but not to this precision. If I want to have more states converged, then I have to calculate for more characteristic roots. The more characteristic roots, the bigger the radius in which eigenvalues will have converged. So if I calculate twice the number of characteristic roots, I see that it takes a little bit longer. I have a new plot, and then I can zoom closer to the imaginary axis to obtain the results, and I see that indeed now all of them have been colored in green, meaning that they have converged, and this time we have those typical eigensets of frequency lifted systems. Something else you can do with the delayed system is, just as for the non-delayed system, is a calculation of a frequency response. So I will keep the AC side example of before, from VG to IS specifically. If I can run it for this one, I see some of the more typical non-passive regions. Again, this is maybe unlike what is usually observed for MMCs, but let's recall that this is a very simplified MMC and that it is also single phase. If I want to obtain the +1 shift transfer function, I just do this, and there it is. I see that its magnitude is much smaller, but at some point you may want to analyze these responses. Matlab tells that the frequency response is infinite at some frequencies due to poles on the stability boundary. Indeed, there is a resonance at 100 Hz. So if I evaluate it exactly at 100 Hz, it is equal to infinity in theory, and so it doesn't calculate properly. There are easy ways to go around that. Just have more points and they will be distributed differently. I have no additional warning, and I see that this time I have been able to calculate a point not at 100 Hz, but just before and just after.